Okay everyone, welcome back. So here's the third lecture of pipeline, about the pipeline. So today we are going to learn about the hazards, the problems that we face while implementing the pipeline. Pipelining is actually, as we have studied in the last lecture, that pipelining is actually very good, very an implementation that improve the performance by a big margin. So that's why all the latest computer techniques, all the latest computers, they actually most of them use pipelining in their hardware implementation. So let's just see what's in it today. So we'll be studying some hazards in pipelining, the problems that we face while implementing. So pipelining is actually good, but it also has lots of problems while implementing. So these are the something that we are going to learn today. So roadmap so far, like always, we are right here at the bottom. Pipelining, data path and control we studied in the last lecture. Now today we'll be doing the pipelining hazards and their solutions. So pipelining hazards, what are the pipelining? Last lecture we introduced the pipeline MIPS processor which executes several instructions simultaneously. They are done in parallel. So each instruction requires 5 stages and 5 clock cycles to complete. After the first instruction is completed, then the next instruction will take one clock cycle. They will be completed in the next every clock cycle. One instruction will be completed. So each stage you have different function units for the database. So all the once the pipeline is full, all the function units are active, and all the function units are basically used by the processor for different instructions in different clock cycles. So today we'll learn about some of the problems that we can actually face while implementing pipelining, and we'll learn how to handle them. So there are actually three types of hazards when we talk about pipeline. First one is structure hazard, then data hazard, and then control hazard. So today's topic is actually data hazard. Just structure hazard, we just see how these things, what these hazard types are. Structure hazard is basically when we don't have enough hardware available for the pipeline operation. For example, just like multi-cycle, if we use a single memory, what happens then? Basically, in multi-cycle we use a single memory instead of two memories in single cycle data path, or in pipeline we use two memory because uh, for for each clock cycle uh, we can only access one memory at a time. So what happens if there is a single memory? Then it will be a hazard. It will actually be a problem when both the memories are needed at the same time for different instructions. That will be a hazard. Then such type of hazard is called structure hazard. A similar case would happen if we have only single ALU, just like multi-cycle. So it will be a problem as well, because we need multiple ALUs for different operation in the pipeline. Similarly, there is a control hazard. What's a control hazard? That is when the CPU cannot decide which instruction to fetch next, because it's a parallel thing. The next instruction is fetched automatically. But what happens if there is a branch instruction and the condition is true for branch jump? So what in the normal operation, it should jump to the branch target address, but due to the normal operation of pipeline, that is already the next instruction has already started before the branch target address branch decision is made in the third clock cycle. So that is actually the case of control hazard that we learn in the next lecture as well. So now today's lecture is all about data hazard. Data hazard is basically a type of hazard that can occur if the instructions are dependent on each other. That means if an instruction needs data that from the previous instruction which has not been updated yet. So this is what we'll do. So let's just go through with the pipeline data path that we studied. So this is something we have got 5 stages. First stage, instruction fetch. The data is stored in IF/ID register. The second stage, ID. The register read are stored in the ID/EX. Similarly, all the control signals are stored in this ID/EX pipeline register. Similarly, the third stage, the result of ALU and the branch target address and all the different things. They are and all the control signals from the second stage second stage that is now transferred propagated to the next stage in the EX/mem register. Similarly, in the next stage, the data from the ALU that was stored in EX/mem that is passed to memory or it's bypassed to the and propagate to the next stage register, which is mem/wb. And in the last stage, this is being and the write back data is actually copied from this mem/wb and stored in the register if it's load word or type instruction. So this is a typical pipeline data path. Let's just go through with the same example that we did last lecture. What happened, this diagram shows the execution of an ideal code segment. So this why we say it's an ideal, because it's all the instructions are independent and they actually need in exactly 5 clock cycles. So this is a typical 5-stage pipeline that we studied for MIPS. So these are each instruction they need 5 clock cycles for completion. The start point of first instruction in the first clock cycle, it will be completed by 5th. After that, the second instruction starts at clock cycle number 2 and it finishes in at clock cycle number 6. Similarly, the third instruction starts at clock cycle number 3 and finishes at clock cycle number 7. Similarly, and so on. So one instruction begins on every clock cycle for the first clock cycle for the first 5 cycles, and after that for every clock cycle there is one instruction that is going to be completed in the write back stage. So basically our examples are very simple, very simple examples. Why? They are independent instruction, no data is basically used. That write data that is the destination of one register. All the data written in the first instruction is used in any subsequent instruction. So this is why all the instructions are independent. So it means we don't need any complication for this pipeline. Let's see, but most sequences they are not independent. Usually when you do programming, you use the data that is generated from one instruction in the next instruction. So let's go through with another example which has some dependencies. So this is an example. Let's just see these. These are 5 instructions. So first instruction is sub with the result is stored in register number 2, 1 minus 3, 1 register number 1 minus register number 3, the result will be stored in the register number 2. Similarly, the next instruction, the register number 2 and register number 5. So AND operation will be between register number 2 and register number 5, and the result is stored in register number 12. So here you can see the register number 2, which is the source for the second instruction. It is actually the destination of the first one. Similarly, for the third instruction, the source is register number 2. Again, that is the destination for the first instruction. Similarly, the fourth instruction also has got the source register number 2, and the fifth instruction is also depends on the register number on the first instruction, which has got the register number 2 as destination. So these are all the dependencies. Some of the dependencies are okay, some of the dependencies are not okay, because in pipelining the data is written in the write back stage. So let's just see how it is a problem. So this is usually not a problem in single cycle or multi-cycle, but it can be a big problem if we are talking about pipelining. So let's see what happened in pipelining. So this is the first instruction. The first instruction, you can see the register number 2, that is actually by the normal operation it is written in the 5th clock cycle. So before the 5th clock cycle, you cannot have this register number 2 as the actual value of 1 minus 3. So the subtraction of 1 minus 3 will have the result 2, but that will be ready in this clock cycle number 5. the data will be stored in register number 2 in only clock cycle number 5. Before this will not be there. But let's see just the second instruction. This is and this register number 2 is basically read in this clock cycle number 3 to be used in the clock cycle number 4 for EEE operation of AND. So what we have here is the register number 2 is not ready yet, but it is needed in this clock cycle number 3. What happens? This is basically a dependency. Similarly, the next one, the data is still not ready, but it is to be read in this clock cycle number 4. So for this third instruction, clock cycle number 4, the register number 2 is read. For the second instruction, clock cycle number 3, this register number 2 is read, but it's still not written yet. It's not yet stored. For the register number 4, for instruction number 4, you can see again the data is written in 5th, and it's actually read in the same clock cycle. So technically we just have this same clock cycle. The data is written at the and it's used in the same clock cycle. So this is also a dependency, but we can see how it's okay or not. The next one, the last store word instruction, that ID, it is basically the data is used in the 6th clock cycle. It is basically read in the 6th clock cycle, which is the register number 2 that was written in 5th. So that is also a dependency, you can see, but this dependency is actually, you can see it's quite okay. So that is after the write back operation. So things that are okay, which of these dependencies are fine? You can see the last one is totally fine. This is perfect. The second last one, this one, the same clock cycle. This add instruction is also okay. Why? Because of the register file design. What happened in the register file? Registers are written at the beginning of the clock cycle, and the new value will be available by the end of the clock. So we need the clock cycle edge. We just need clock cycle edge for write operation. For read, we don't need anything. So it means if the data is written at the start of the clock cycle, it can be used or read at the end. So the store word instruction has no problem at all, because it reads after the subwrites for register between the first instruction. So these are the few dependency arrows. You can see the red ones are the dependencies which are the problems, which are called hazard. These are the this is actually the cases of data hazard, because the data is still not ready and it is used for the next instruction. And the black ones, these are also the dependencies, but they are not hazard, because they are actually okay. A more fancy pipeline diagram, the same diagram. Here you can see the source, the actual location of the data, where the registers are. So the fifth clock cycle, the data is basically write back stage. The data is written in the register file, and the next instruction, it is read in the register file. In the next instruction is read in the register file. Similarly, the fourth and fifth one. So that may be a bit helpful if you visualize where the data is going. A more detailed look, let's just see how the pipeline works. We can see here the data. Okay, sorry. We can actually we see that for any instruction, for a sub instruction, the operation 1 minus 3, register number 1 minus register number 3, that will be done in this third clock cycle, which is the EH stage. For example, this is the third clock cycle where the data is the subtraction operation is done, and that data is basically at this point. So that means the data that is going to be stored in the register number 2, that is right now, that is actually processed or completed in this third clock cycle. So and it is stored in the fifth clock cycle. And similarly, the AND instruction, the AND operation between register number 2 and register number 5, that is done in this fourth clock cycle EX stage. Similarly, the OR operation is done in the fifth clock cycle or EX stage of the fifth one. So sorry, this is where this register number 2 is used in the fourth clock cycle and the fifth clock cycle for the next instruction. So this is something that can be helpful in designing our process, that we can avoid any extra delays if there is a dependency like this. We can bypass the register file, we can bypass the actual write back operation, we can use the data that is stored in the previous stage or EX, the result of EX. We can actually bypass that other stages and just use that data for the computation in the next clock cycle. How? This will be an interesting thing. The data is actually calculated in the subtraction of 1 minus 3. This is actually done in the third clock cycle. We can use this data in this next clock cycle. If we just get the data output from the EX directly to the input of EX, we can use this data for the next instruction. Similarly, for the next one, the third instruction, this data which is the result of the sub instruction, the result of 1 minus 3, for the next instruction the result will be actually be passed to the next clock cycle. Why? We can actually we cannot use the output of EX. Why? Because the output of EX will now have the value of AND operation in the last instruction. For the OR operation, the input of EX has to be register number 2, the value of register number 2, and that value of register number 2 is actually at this memory, at the output of memory stage, or the register or the pipeline register at the output of. So this will be we can use those data, either the output of EX stage, if we are moving or if we are forwarding this data from the first instruction to the second one, we can use the data from the output of EX. If we are forwarding the data from the first instruction to the third one, we have to move the data or forward the data from the output of MEM to the input of EX. So these are the two different scenarios for these. Similarly, if we have got load word instruction, it will be a totally different thing. Why? Because the data is not the data to be written back, it's actually ready, it gets ready after the memory stage for load word instruction. So it means we cannot move the data from EX. So this will be a little different, that we'll study in the next part of this lecture. So where to find the ALU result? We know that in the third stage, if we are moving the data from the first instruction to the second one, the result is basically stored in EX/mem register. The output of ALU will be in this EX/mem register. That means the result is here. But if we are using the data from the first instruction to the third instruction, it means that data has already moved to the next pipeline register, which is mem/wb. So these are the two cases where in these two dependencies, the data is either in the EX/mem register or is in the mem/wb, and after that data will be written back in the register file. So this is the final one. But before that, the data is actually stored in the in this third clock cycle, it is generated. In the fourth clock cycle, it is already stored in EX/mem. In the fifth clock cycle, it is in the mem/wb register, and after that it is written in the actual register. So we know that for in every clock cycle where the data is there. So how to forward this data? We just move the data from the respective, from the actual case where the data is present. So for the first instruction, when the first instruction is in the fourth stage, that is in the result is stored at the ex memory register. The output of ALU is actually stored in this at the output of ALU. So this ex/mem register will have the result of ALU that can be forwarded to the input of the ALU. So this data is basically gone back for this next ALU. So for the next operation in this second instruction. Similarly, the third instruction also needs the register number 2, but now this register number 2 is already passed on to this mem/wb register that we saw here. So in the next clock cycle, this data is in this register. So this register mem/wb will have register 2 that will be transferred to the respective input of the ALU in the for fifth clock cycle. So this is how we actually do the forwarding. So if there is no header, the ALU operand will come from the register file. These are the different. There has to be a forwarding unit. There has to be a hardware that actually detects and generates the actual forwarding unit. If there is no header, there are different cases. There are first simple cases. If there is no header, that means the normal operation will be done. So data will be taken from the register file as normal operation. If there is a forward, it means the data will be taken from either this blue register, which is ex/mem, or this green register, which is the mem/wb. If we are moving the data from the first instruction to the second instruction, that means the forward is if the second instruction depends on the first, we have to move the data from this ex/mem register. Or if we have got the third instruction that is dependent on the first one, we need the data from the green register, mem/wb register, which will be moved to the register for input of ALU for forwarding. So how to get the forwarding done, how these ALU inputs are decided, we'll go back to the same old scenario. How to set up the ALU inputs? We will use extra bigger multiplexer to do the to select between the different inputs, and these extra special control multiplexer will be used to get the data from forwarding, the data used for forwarding. So which data is to be used, it will depend on the specific control unit, forward A and forward B, that will decide which data to be used. 0 means the normal data. This 1 means the data is to be forwarded from mem/wb, that is like the first to third dependency. And if the value is for both forward A and B is 2, it means the result will be copied from the second the ex/mem. That means the dependency is from instruction number 1 to 2. So this is how a typical multiplexers will actually decide the inputs of ALU. It's just taking that value from the outputs of the ex/mem and mem/wb. That means the previous instruction will have the data ready by by the same time. So how to detect the ex/mem data hazard. How do we detect the data? We should know the reason before this time. This forward A and forward B should be generated from some kind of control unit that detects the whole forwarding. So how to know that? We know that the instruction is fetched. Every instruction is fetched at the first stage. We know which instruction has got dependency. How do we know the dependency? We know the RS, RT and RT values. If we know that the RS or RT values of a subsequent instruction, RS and RT, if it's the same, if the number of the registers or the address of the register or anything that is from your current destination register. For this is basically R type instruction, so that means the current instruction RD value, if it is equal to the next instructions or S or RT value, it means this is some kind of header. Which hazard? So it will be either ex/mem hazard. Ex/mem hazard means that is the exactly next instruction. So instruction 1 to 2, if the instruction number 2 is depending on instruction number 1, it means it's an ex/mem header. If there is a mem/wv, there is another type of header which is like the mem/wv header. What happened there? The instruction number 1 is basically, instruction number 3 is actually dependent on instruction number 1. That will be a mem/wv header. So let's just see how to detect the first instruction, the ex/mem header. That means the first, the second instruction is dependent on the first one. So where to get the control signals? We know that the first instruction is basically the sub instruction. The sub instruction is in the second stage. So at the end of second stage, this ex/mem dot register write. So we are just checking if the ex/mem dot register RD. So the RD register of the current instruction, that is the sub instruction, if it is equal to the ID/ex, what instruction will this ID/ex register will have? It will be the next instruction. So if the current instruction RD value is the same as the next instruction RS value, then it means forward is has a value of 2, that means ex/mem header. And same in the case for RT. So if the current instruction RD is equal to the next instruction RT, it means the forward B should be equal to 2. So that 2 means that ex/mem is forwarding. So it's very simple like this. Similarly, if we have got a case when the similar case when we have this instruction where the first instruction, the third instruction depend on the first one, it means the first instruction has to be at m/wv. So this is the first instruction which is in the fourth stage, and the third instruction is in the ID/ex stage. So this means, so the same check will be there, but what we have here is, so the check will be the first, the mem/wv, the RD register, is it equal to the current instruction ID/ex RS or RT, then the case is there. But there is another special case for mem/wv header. Why? Let's just see this another new example like this one. Now there are actually two dependencies. The third instruction depend on both instruction number 2 and instruction number 1. So the third instruction depend on both register number 2, instruction number 2 and instruction number 1. Now what happens? So both the cases are there. The ex/mem header is also there. The mem/wv header is also there. So which header to consider then? We can see, we know that the latest data, only the most recent data. So this data is what we should be using for the next instruction. So it means the last instruction or the ex/mem has the priority here. So ex/mem is actually the high priority header. If both memory header, mem/wv header is there, and ex/mem header is there, we can always skip the mem/wv and we use the ex/mem. So that will be done. So this is the memory/wv header equation. So it will add another check, and that check is basically if there is no ex/mem header. If there is no ex/mem header, that means it's a normal case of memory/wv, or register number, or the instruction number 3 is dependent on instruction number 1. It means the forward A is equal to 1 only if there is no ex/mem header. So this will be the case for mem/wv headers. So there will be a forwarding unit here. This forwarding unit will decide that which forwarding case we have got. Either it's a normal case or some kind of forwarding case. The data is basically passed from the if/id stage, ex/id/ex stage. So all the stages have got the instruction control signals coming from the opcode that will from the instruction that will decide what type of cases should be done. So the forwarding unit, it has several control signals as input. It has got the rs and rt from id/ex, from ex/mem, and from mem/wb. So it means if this is your instruction number 2, this will be instruction number 2, and this will be instruction number 3. So instruction number 1 will be at mem/wb, instruction number 2 will be at ex/mem, and instruction number 3 will be at id/ex. So this is how your forwarding unit decides. So the two register write signals are not shown, but they come from the control unit, like just like your typical ones. And we have this forward A and forward B deciding what the source of your ALU should be. So let's see just again the same similar example. We just finished this today's lecture with this example. So what to do there? We have got a sub instruction, the same instructions, the same operation here. We'll see how it works. So again, assume the register initially contain the number plus 100. The register number, if it says register number 2, it means 102 will be the value. After the first instruction, the 2 should contain -2, because this is 101 minus 103. The other instruction should all use the -2, because that -2 is the result that is needed, not the previous one that was 102. So this is something that we need. So we don't have memory that is needed, but if we had, we can use the same. And we also skip the first two cycles because they are the same. Now come to the third clock cycle. What's happening in the third clock cycle? This EX stage is basically where the data, the result of the sub instruction is done. So sub instruction result is -2, because 101 minus 102 is 103 is -2. This is now stored at this register. So this is important. And the next instruction, we actually read this register number 2 here. So register number 2 is basically read and is passed to the next clock cycle, just like the typical operation. And for the next instruction, it will be done similarly. So now in the next stage, we need forwarding. Why we need forwarding? Because it's a case of a forward, and this forward A block is actually checking if the id/ex rs, which is 2, is it equal to the last instruction ex/mem rd, which was 2. So this is equal. It means that we have to do the forward 2. Why we need forward 2? Because we have to get the forwarding from this ex/mem register. Otherwise, by normal operation, it would have taken the 102, the original value of register number 2. So it will not take 102. It will in fact take -2, which is stored in the last register. So this value will be passed to this ALU, and the result will be computed. Similarly, the next instruction is already here. It also needs register number 2, but again this is something that will be used in the next instruction. Now this first instruction is in the last stage, fourth stage, where the register number 2, the value of register number 2 -2 is actually at this register mem/wb. This ex/mem has the output of ALU, which is the result of OR operation 6 and 2. So whatever that result is, that is stored here. And the next instruction id/ex needs this value. So first in this ALU, we need the value of 2. Where should this value of 2 get from? Either it is coming from register, or it has to come from ex/mem or mem/wb. So which value it needs? It has to come from mem/wb. Why? Because the first instruction result is actually at this point. so it will not get the result from the EX/mem. So this, in this case, the forward B will be, because it's now forward B in the second operand of this instruction. So this is basically getting the data from MSIWD and compute the result accordingly. So, and this will complete the process normally. So there are lots of data hazards we have got. The first data hazard occurs during the cycle 4. The second data hazard that occurs in the cycle 5. There are no hazard involving the sub instruction. During the cycle 5, sub writes a result back into register number 2, and the next instruction, add instruction, actually can read the register accordingly for the next one. So this is actually how a typical this forwarding unit works, and the complete data path, the pipeline data path including the forwarding unit. So still few things missing, but this is the complete data path so far. Some miscellaneous concepts: each MIPS instruction writes at most one register. It's still we introduce some complexity, but still it's a very simple one. New instruction, you can check out some new instructions in the exercise. We'll actually do in the discussion as well. So we'll do some example from the exercise. So this makes forwarding hardware easier to design, because there is only one destination register that ever needs to be forwarded. That for R type instruction, the RD register is the destination, but if we use the load word instruction, it will be a little bit different, a bit more complicated than the simple R type. So forwarding is especially important, because we can see by using the forwarding, we can skip any extra delays for this typical operation, even if the next instruction depends on the previous one. But that is not possible if we have got a load word instruction. Just check out the how it works. Read the header section from the book. It will be much easier, because not everything is discussed in the lecture. You can learn a lot from the book. You can do some example and exercise. So in real code, most instructions are dependent upon other ones, and that's where the data hazards come from. The forwarding eliminates data hazard involving the R type instruction. Forwarding may be helpful in the load word instruction, but it will be a little bit more complicated. So next time we'll be finishing up the pipelining with the load word instruction data hazard, as well as the control hazard for branch. So until next time, bye bye.